Hello, students. Mr. Madison here, and this is the second in a series of videos designed to teach you how to find area of circles and parts of circles. We've already learned how to find the area of a circle, and this video will focus on finding the area of what's called a sector of a circle. So let's make sure everybody knows exactly what it is we're trying to do. Our objective here is to be able to find the area of a part of a circle called a sector. So by the end of this video, everyone will be able to do exactly that. Let's start by making sure we all know what a sector is. It's not a word. It's a word that we've used before, so it should not be completely unfamiliar to you. But I'm going to draw a circle. And in the circle, I'm going to draw a central angle here. Now, when you look at this, you might liken this figure to a pizza, a circular pizza. And when you slice a pizza, by cutting the pizza using diameters that go through the center, each slice of pizza is a sector. So if you need something to help you remember what a sector is, it's the part of a circle that's in the shape of a slice of pizza. So this central angle is going to have a certain degree measure, which for right now I'll just assign it X degrees. And then you're going to have a radius, and this part of the circle that I'm shading on right here is called the sector. Now the sector, the area of a sector is going to always equal some fraction times the area of the circle. If you cut the pizza into 8 equal slices, then each slice would be 1/8 of the pizza, or 1/8 of the circle. If you cut the pizza into 12 slices, each slice would be 1/12 of the pizza. So we need to first of all determine how this fraction comes about. Well, if you look at the degree measure of that angle, and you know that there's 360 degrees all the way around the circle, then that fraction is very simply going to be the degree measure of that central angle divided by 360. The area of a circle, we already have a formula for that, pi r squared. So the area of a sector then, the area for a sector is given by this formula. It's going to be the degree measure of the angle over 360, that creates that fraction, and then you multiply by the area of a circle. So let's do some example problems. Here's a 40-degree sector. And I'm going to shade that in. Now I want to introduce to you some notation. Look at this. A for area, and then subscript, I'm going to put SR. SR stands for shaded region. So this symbol right here means area of shaded region. And when you're doing these types of problems, what's going to happen is part of the diagram is going to be shaded. And that's the part you're going to be finding the area for. Also, look at this notation. A for area, and then UR. UR stands for unshaded region. So this would be the area of the unshaded region. Sometimes you'll be asked to find the area of the unshaded region. You know, it goes without saying, but I'll probably say it anyway. If you add the area of the shaded region to the area of the unshaded region, that would give you the area of the entire figure. Keep that in mind, because sometimes all you'll have to do to find one of these two values is to subtract the other one from the area of the entire figure. So let's go on here. Let's suppose I tell you that the radius of this circle is 12 inches. And we want to find the area of the shaded region. The shaded region is a sector. The area of the sector is a certain fraction times the area of the circle. The fraction would be the degree measure of that arc. That's a 40-degree central angle and a 40-degree arc. So it's 40 divided by 360 times the area of the circle, which would be pi, times the radius, which is 12 squared. Now, at this point, I'm going to go ahead and write down the pi, because I'm going to find my answer in terms of pi. There will not be a need for this problem to multiply by pi. The pi is just going along for the ride. It's going to be there as part of my answer at the end. But I have to do some arithmetic here. Now, if you're going to do this in your calculator, which is fine, you're going to do 40 times 12 squared divided by 360. And that'll work out just fine. I'm going to do just a little bit of arithmetic here without the calculator. I know 40 out of 360 is 1/9. And then sometimes for 12 squared, I'll just write 12 times 12 if that's okay. And then I know that 3 goes into 9 3 times, and it goes into 12 4 times. And 3 goes into 3 once, and it goes into 12 4 times. So all that's left for me to multiply after I cancel out all the common factors is 4 times 4 times pi. So answer is going to be 16 pi is your answer on this problem. 16 pi would be the area. Now, since it's 12 inches, it's actually going to be inches squared. Inches squared is the final answer. Let's do another problem here. Oh, by the way, you know, I had given you this symbol for unshaded region. If I wanted to find the unshaded region here, then here's what I would do. Unshaded region would be basically the same exact equation or the same exact expression that I have here, with the exception of the 40. So the number on top, when I find the unshaded region, wouldn't be 40. It would be 320. The 320 is derived by subtracting the 40 from the 360. So this arc from here all the way around would be 320. So this would be a 320 degree sector here. So I then multiply by pi times the radius squared times 12 squared. And that would give me my answer. But let's think about this for a second. The radius of this circle is 12. So the area for the entire circle, would be pi times 12 squared, which would be 144 pi. That would be the entire thing. We already determined that the shaded region is 16 pi. The unshaded region then would have to be the area of the whole circle minus the area of the shaded region. The area of the whole circle is 144 pi. I would then subtract 16 pi, and that would give me 128 pi for the area of the unshaded region. And I would bet you that if you did this calculation right here, 320 over 360 times pi times 12 squared, you're going to come up with 128 pi. And to be honest, this first method for finding the unshaded region should make complete sense, but also this secondary method where you subtract the shaded region from the circle to get the unshaded region, that should make sense to you as well. All right, let's go on. Here's another circle. And I'm going to say that this central angle right here has a degree measure of 120. And I'm going to tell you that the radius for this circle is 15. But I'm going to shade this part of the circle here. And I'm going to be asking, what's the area of the shaded region? You just have to be careful. You know 360 goes on the bottom here to get your fraction. But what number goes on top? Not the 120. 120 would be the degree measure for the unshaded. The number that has to go on top here would be the degree measure that corresponds to the shaded. And I hope that it makes sense that I'm going to put 240 there. And then I need to multiply that fraction by the area of the circle, which would be pi times the radius, which is 15 squared. Now, once again, I'm just going to have a pi in my answer. And then to get your number in front of the pi here, you could put this in your calculator. 240 times 15 squared divided by 360. So I'm going to maybe do a little bit of math here, arithmetic without the calculator. 240 out of 360 would be 2/3. And I have to multiply by pi times 15 times 15. So 3 goes once and 3 goes 5. And 2 times 5 is 10 times 15 would be 150 pi, and I'm home. So on this problem, we're given the degree measure for the unshaded region, but we're asked to find the area of the shaded region. So this number on top we get by subtracting that 120 from 360. Let's do another problem. Let's see if we can get one that's maybe a little tricky. I'm going to draw in a diameter. And I'm going to make an angle over here of, say, 60 degrees. And I'm going to make an angle over here of, let's say, 40 degrees. And I'm going to shade this 60-degree sector, but I'm also going to shade this 40-degree sector. And I'm interested in finding the area of the shaded region. Well, you know what? I guess we could find the area of the 60-degree sector and then find the area of the 40-degree sector and then add those two together to get our answer. But I think what I'll do is, instead of thinking of this as two separate sectors, I'm going to kind of merge them. And my number on top, I'm going to make 100. A 60-degree sector and a 40-degree sector have the same combined area as a 100-degree sector. And then times pi. I need a radius here. I'm going to go ahead and let the radius be 36 inches. So times 36 squared. All right, so I'm going to go ahead and maybe do a little arithmetic. I know 100 out of 360 is 5 out of 18 times pi times 36 times 36. Now 18 goes once and 18 goes twice, and 5 times 2 is 10 times 36 would be 360, and the pi guy is going along for the ride, and I'm done. Now, this arithmetic that I'm demonstrating here, you do not have to do that. You can just go right to your calculator, do 100 times 36 squared, then go divided by 360, and you'll come up with 360 pi for your answer. All right, let's do another problem. All right, let's see. This problem is going to be a little different. It's going to be a little different because we're going to be solving for one of our variables in our formula. So I'm going to tell you right off here that the area of the shaded region is 49 pi. And we'll say that's inches squared. So we're given the area of the shaded region, and we're going to solve for R. What's R? That's the question. So here's our diagram. So I'm going to start by writing my formula. The shaded region is a sector. So the area of the shaded region has to equal x over 360 times the area of the circle, which would be pi times the radius squared. The algebraic approach here is to plug into the formula the information we have and then solve for R in this case. So the area of the shaded region is 49 pi. So I put that in. X is 90 times pi times the radius squared. All right, algebra skills. The pi's cancel. That corresponds to dividing both sides of that equation by pi. Now I need to isolate R squared. So I'm going to write down this 49, and I'm going to multiply by the reciprocal of 90 over 360. So I got to multiply by 360 over 90, and that will isolate R squared. So I'm just going to go to the calculator, and I'm going to do 49 times 360 divided by 90. And I'm coming up with 196 for R squared. But my job is to figure out what R is. So what I would do now is I would merely take the square root of both sides of this. The square root of R squared is R, and that's why we did that. 196 is a perfect square. It's 14. And we're home. So let's review this problem before we do another one. In this problem, we were given the area of the shaded region, and we were asked to find R. So we wrote our formula. We substituted into our formula the values we were given, which were the arc length and the degree measure of the angle. Then we isolated R squared, and our final algebraic maneuver was to take the square root to figure out what R is. Let's do another problem. This problem has a 72-degree central angle here. and r is only given as r, so we don't know r. And this part of the circle is shaded. Here's what we know. We are given that the area of the shaded region is equal to 500 pi. And we are asked to solve for r. So, just like the last problem, I'm going to start by writing down my formula. I'm going to write down that the area of the shaded region is equal to x over 360 times the area of the circle, which is pi times the radius squared. I'll substitute in what I am given. The area of the shaded region is 500 pi, so I've got 500 pi equals. Now you need to be careful. The shaded region does not correspond to that 72 degrees. The shaded region would be 360 minus 72 degrees, which would be 288. It's important for you to put 288 right there. And it's important that you understand why we're putting 288 right there. It's because the shaded region is a 288 degree arc. The part of the circle that's shaded is 288 over 360 times pi times the radius squared. R is what we're looking for. The pi's cancel. I'm going to write down that 500. I'm going to multiply by the reciprocal, so I'd be multiplying by 360 over 288, and that would isolate r squared. I'm going to go to my calculator, and I have 500 times 360 divided by 288, and I'm coming up with 625 is equal to r squared. Take the square root of both sides, and you'll have your value for r. The square root of 625 is 25. And we're done. Let's do a couple more problems. Let's see. In this problem, we are told that the area of the shaded region is equal to 135 pi over 2. And we're asked to solve for x here. So in this problem, we do not know the degree measure there. So we're going to take the algebraic approach of writing down our formula and substituting into the formula what we know. So the arc length, the area of the sector, would be the area of the shaded region, is equal to x over 360 times the area of the circle. So that would be times pi times r squared. We're given area of the shaded region, so I'm going to put in 135 pi over 2. And that has to equal x over 360 times pi times 15 squared. To solve for x here, the first thing I'm going to do is cancel out my pi's. And I'm going to write down this 135 over 2. Now, to get rid of this 360 over here, I have to multiply by 360. And then to get rid of this 15 squared, I'm going to multiply by 1 over 15 squared. And that will isolate the x. So I'm going to my calculator, and I will talk through what I'm keying in. So I'll have 135 times 360. And I'm going to go ahead and hit enter. Then I'm going to go divided by 2, enter, divided by 15 squared, enter. And I'm coming up with 108 degrees for x. So let's look back at what we've done. We started this lesson by formulating the area of a sector expression here. The area of a sector, of course, would be a fraction times the area of the circle. The fraction is the degree measure of that central angle, or the degree measure of that arc that central angle inscribes or intercepts. So what we did here was we took this 40, which was our value for x. We took 12, put it in for r, and then we did our arithmetic and we found our answer in terms of pi. And then I made mention of the fact that to find the area of the unshaded region, you could do a subtraction problem. The deal is that if the shaded part here is a 40-degree sector, then the unshaded part would be a 320-degree sector. In this problem, we were asked to find the area of the shaded region, but the degree measure that we were given corresponded to the unshaded region. So to figure out what number to put on top when we're forming our fraction, we subtracted that 120 from 360. In this problem, we are trying to find the area of actually two sectors, but instead of doing it as a two-part problem and then adding the parts together, we went ahead and merged together the 40-degree and the 60-degree, and we just said we're going to find the area of a 100-degree sector. Then we started to get into some problems where we already knew the area of the sector, and we were asked to find either the radius or we were asked to find the degree measure of that angle. And the approach there is simply to write out your formula each time. You can see that's exactly what I did here, here, and here. I just wrote out the formula each time and then substituted into the formula the values I was given, and then used my finely honed, highly honed algebra skills to isolate whatever variable I was asked to find. So students, our objective was for everybody to be able to find the area of a sector. And I'm hopeful that we've accomplished that, and I'm hopeful that my explanations here are clear to you, and that we're good to go on problems that ask you to do just that. And that's what you can expect on your next practice. So I thank you for your attention. You all have a great day.